Albert Einstein helped build quantum mechanics. He is one of the architects of the theory. Then he spent the last decades of his life arguing that it was incomplete. This is not a story about a scientist falling behind. Einstein understood quantum mechanics deeply. He challenged it not because he failed to grasp it, but because he believed it failed to grasp reality. The disagreement was not about math or experimental results. Quantum mechanics made accurate predictions, and Einstein never disputed that. His objection was philosophical. He believed that a complete theory of nature must describe what actually happens, not merely what can be measured. He believed the universe operates according to definite, knowable laws, even when those laws are hidden from observation. That belief put him in direct conflict with the generation of physicists he had helped to create. To understand why Einstein rejected quantum mechanics, it is necessary to understand how central he was to its creation. In 1905, Einstein explained the photoelectric effect. When light strikes a metal surface, it ejects electrons. Classical physics could not account for why this happened only above a certain frequency, regardless of intensity. Einstein proposed that light arrives in discrete packets, not as a continuous wave. He called them quanta. Each packet carries energy proportional to its frequency. This single idea, light behaving as a particle, was one of the foundational moves in quantum theory. Einstein did not stop there. Throughout the 1910s and 1920s, he contributed to the specific heat of solids, applying quantum reasoning where classical physics failed. He contributed to the theory of stimulated emission, which later became the basis for lasers. He helped establish the statistical framework that described how particles behave at the quantum level. Quantum mechanics, as it emerged through Heisenberg, Schrödinger, Born, and Bohr, was built on foundations Einstein had laid. Without his photoelectric explanation, the field would not exist in the form it took. Einstein was not an outsider criticizing quantum theory. He was one of its founders. By the late 1920s, quantum mechanics had a coherent mathematical structure. It could predict the outcomes of experiments with extraordinary precision, but the interpretation of that structure was deeply unsettling. The theory described particles not as objects with definite positions and velocities, but as wave functions. A wave function encodes probabilities. It does not say where a particle is. It says where a particle is likely to be found if measured. Before measurement, the particle does not have a definite location. It exists in a superposition of possibilities. Werner Heisenberg formalized this in his uncertainty principle. Certain pairs of properties, such as position and momentum, cannot both be known precisely at the same time. This is not a limitation of instruments. It is a fundamental feature of nature. Max Born established that the square of the wave function gives the probability of finding a particle in a given state. Quantum mechanics was, at its core, a probabilistic theory. It did not predict exactly what would happen in any single event. It predicted the statistical distribution of outcomes across many events. For Einstein, this was not merely unusual. It was a fundamental problem. He drew a sharp distinction between prediction and explanation. A theory that predicts outcomes without explaining why those specific outcomes occur is, in his view, incomplete. He believed that beneath the apparent randomness of quantum mechanics, there must be deeper, deterministic laws not yet discovered. The central figure in defending quantum mechanics against Einstein was Niels Bohr, a Danish physicist who had used quantum ideas to explain the structure of the hydrogen atom. By the late 1920s, he had become the leading voice for the Copenhagen interpretation. This view held that quantum mechanics was complete. The wave function was not a stand-in for something more fundamental. It was the most complete description of reality that could exist. A particle genuinely did not have a definite position or momentum until it was measured. Probability was not a gap in knowledge. It was the nature of reality. Bohr argued that the demand for a deeper deterministic explanation was a holdover from classical thinking. At the quantum level, the rules of the physical world simply operated differently. Accepting this required abandoning certain intuitions, but those intuitions were not justified by evidence. Einstein disagreed. He famously stated that God does not play dice with the universe. This was not rhetorical flourish. It was a precise expression of his conviction that nature is deterministic at its foundation, that every event has a cause, and that a theory which cannot account for causation is unfinished. The debates between Einstein and Bohr continued through the late 1920s and into the 1930s. They took place at conferences, in correspondence, and informal published exchanges. Einstein repeatedly designed thought experiments intended to show that quantum mechanics led to contradictions. Bohr responded to each one, demonstrating that the theory held up under scrutiny. Neither man changed his position. Einstein's most rigorous challenge to quantum mechanics came in 1935, in a paper he co-authored with Boris Podolsky and Nathan Rosen. The paper is known by its author's initials, EPR. The EPR argument was constructed carefully. The authors proposed a scenario in which two particles interact and then move apart. Quantum mechanics predicts that measuring a property of one particle instantly determines the corresponding property of the other, regardless of distance. If one is measured and found to have a certain spin, the other is immediately found to have the opposite spin, even if separated by vast distances. Einstein found this conclusion unacceptable. It implied that physical events could influence each other instantaneously across any distance. This violated what Einstein considered a basic principle of nature, local realism. Objects are only influenced by their immediate surroundings, and no information or influence can travel faster than the speed of light. The EPR paper argued that quantum mechanics therefore could not be a complete theory. Either the two particles carried definite properties from the moment they separated, properties that quantum mechanics failed to describe, or the theory was allowing for instantaneous influence that should not exist. He believed a more complete theory would eventually reveal them. Quantum mechanics, in his view, was accurate but not final. For decades after the EPR paper, Einstein's position could not be tested. The debate remained theoretical. That changed in the 1960s, when physicist John Stuart Bell published a mathematical theorem that transformed the question into something experiments could answer. Bell's theorem showed that if hidden variables existed, if particles carried predetermined properties, as Einstein believed, then the statistical correlations between measurements on separated particles would obey specific mathematical limits, called Bell inequalities. If quantum mechanics was correct, those limits would be violated. Beginning in the 1980s, a series of increasingly precise experiments tested Bell's inequalities directly. The most significant early tests were conducted by Alain Aspect and colleagues in France. Later experiments closed remaining loopholes and confirmed the results with greater certainty. In every case, the experiments showed the same outcome. Bell's inequalities were violated. The correlations between particles were stronger than any hidden variable theory could produce. Einstein's preferred alternative was ruled out by direct experimental evidence. The experimental defeat of local hidden variables did not resolve every question Einstein raised. The interpretation of quantum mechanics remains an active area of debate. Multiple interpretations compete. The Copenhagen interpretation remains influential, but is not universally accepted. The many worlds interpretation suggests that every quantum measurement causes the universe to branch into multiple outcomes, each one real. Pilot wave theory reintroduces determinism, but abandons locality. Each interpretation is consistent with the same experimental data. The question of whether the universe is fundamentally deterministic or probabilistic has not been settled. What has been settled is that any deterministic account cannot rely on local hidden variables. Einstein's specific proposal has been eliminated, but the tension he identified between a theory that predicts and a theory that explains remains unresolved. Albert Einstein did not reject quantum mechanics out of ignorance or stubbornness. He rejected a specific interpretation, the claim that nature is fundamentally random and that no deeper description is possible. He believed that physics should describe reality as it is, not merely as it appears under measurement. He believed determinism was not an assumption to be discarded, but a principle to be defended until evidence demanded otherwise. He held that position with full knowledge of the theory's success. History has shown that Einstein's particular alternative was wrong. Local hidden variables do not exist. But his insistence on asking whether quantum mechanics was complete, rather than simply accepting its success, was not a failure of scientific reasoning. It was an expression of it. Einstein's disagreement with quantum mechanics was not a footnote in the history of physics. It was one of the most consequential intellectual exchanges of the 20th century. It shaped how the theory was tested, how its meaning was debated, and how physicists continue to grapple with the nature of reality.